All right, so we're going to start with section 4.2, where it talks about relative extreme points, and take a look at how we use the calculator to find those relative extreme points. And there are a couple of ways to do that. So I'm going to use the example that's x cubed minus 8x squared minus 6x that's in section 4.2 notes. And it asks you to find the derivative first, and then it asks you to find the relative extreme points. So we find the derivative on part A to be 3x squared minus 16x minus 6. And what we talk about in this video is the fact that the original graph's relative maxes and mins will occur at the derivative graph's locations of x-intercepts, or places where they cross the x-axis. So what we're really looking for is where that second line, that y2, actually crosses the x-axis. And so we'll say that it's going down to 0. It's crossing the x-axis at 0. So we actually can take a look at that in the window. I don't know what kind of window is actually going to be good to find this. Let's just do a standard window zoom 6 and see kind of where we are. Okay, so there's the original graph, and then there's the derivative graph. And it looks like that the derivative graph is actually crossing, man, I'm not sure what I saw there. It looks like it's crossing several times, but it's also between maybe like -2 and over here. For right now, let me just turn the y1 off because we don't really need to graph it, and maybe it'll help to see the other piece. So here's where it's crossing, and then here's where it's crossing. Those are the two locations that I want. So I can find that intercept and this intercept by doing second calc, and we're doing number 5, intersect. And the equations are in y2 and in y3. So it says y2 is my first curve, y3 is my second curve, and then for guess, I just need to be nearby this particular point, which I am. And there's the x value, -0.352. And I can do the same over here. I can do second calc, and I can do intersect. And again, y2, y3, but then I need to be over here. You can arrow over here. That's one way to do that. If you want to make your arrows jump faster, you can hit the second button and arrow to the right, and it gets there more quickly. Anyway, once we get close enough, there's the other value. It's at 5.685. So those are the values, and then you can just plug them back into the table to find the corresponding y output values from y1. So like this one, 5.685. If I turn y1 back off and I turn this on, I can put 5.685 here, and there's the output value for the minimum point that we were looking for here, or the maximum point, depending on which one you were looking at. So that's how I find maxes and mins. If you take a look at section 4.4, it starts talking about inflection points. And inflection points happen when the second derivative is equal to 0. So we would take another derivative here, right? So I would take the derivative of 3x squared, which would be 6x, and the derivative of -16x, which would be -16. And I would look for where this one crosses the y-axis, the x-axis, excuse me. So I don't know if the window's still going to be any good. We'll just graph it and see, but we're looking for it to cross, and in fact, it's actually really good, crossing right here. So again, we can go into the table. Into the trace button where it finds intersect. This is now in y3 and y4, and since it's only crossing once, I don't even have to be close to the curve. I can just press enter. Hang on, I don't know what I did wrong. Let me try it again. Intersect. So it's y3. We're going to press enter. Oh, I don't have it in there yet. That's right. There was a 0 I need to put in there, so let's try it again. One more time. All right, intersect. First curve y3, there's my second curve y4, and then for guess I can just press enter and it tells me it's at 2.667. And then if I turn my plots back on, I can actually go into the table and put in 2.667. I can tell you that the output of the original function at that point was -53.927. I can also tell you that the derivative at that point was -27.33 repeating, right? So those features are very valuable. All right, the last thing I think that we're going to be talking about in this section is what happens in chapter 5 when we do antiderivatives. So let's go back to this original equation. We're just going to keep what's in here. And let's say that we wanted to find the antiderivative of this instead. I didn't have my graph done very well before. It's just a -10 to 10 window. Let's look at it again, and we'll manipulate it a little bit. Let me actually go in and use the calculator, the values that we have in section 5.8. I think that'll actually make it a better picture. Excuse me. So in 5.8, the first example, is 0.0388x squared. 3, there we go. 388, there we go. Cubed, in fact, not squared. My goodness, minus 0.495x squared plus 5.698x plus 43.6. And it actually tells you from 1990 to 2001, and it's measured after 1990. So the window is going to go from 0 to 11. And if we hit zoom 0, that's zoom fit, it will adjust the y-axis to be a good window for our x-axis that we picked. I'll manipulate it just a little bit because I'd kind of like to see how it's dotted down here? That means that the x-axis is not there, it's further down the screen somewhere, and I'd kind of like to see it. So I'm going to make my y minimum actually 0 so that it will shift it and I can actually see the x-axis. Now here's the cool thing that I wanted to show you, like technology-wise, is that if you wanted to find the area under this curve, there's actually a way in your calculator to do that both visually here and back in the regular screen. So let me show you back in the regular screen first. If you remember, we did a function called Math 8 earlier in an earlier video. Math 9, function integration, is what I'm going to do right now. Much like that when you have to tell it that you want the y equation, you want the variable x, and we're going to go, I'm just going to go from, just so I can see the full screen, I'm going to go from 1 to 10. So we're going to go from 1 to 10, which is not exactly what your problem in your book or in your notes is doing, but just humor me for a moment, 1 to 10. And if you hit enter, it'll actually calculate the area under the curve exactly, at least as it approximates it in your calculator. If your screen doesn't look like that, it will instead look like this. And if that's what it looks like, then right here you put your lower limit for x. So for us, that was number 1, right? Here you put your upper limit for x. Again, for us, that was 10. Right here, you tell it y1, because that's your equation, and right here you tell it x because that's your variable, okay? So that's how you would enter it if this is how your calculator displays that Math 9 feature instead. But here's what I really want to show you. I really want to show you what happens in your graph when you do this. So here's my graph. There's another place to do this, and you see here it says calc here. So if you hit second calc, and if you look at number 7, it actually looks like that same notation we've been using. And you tell it lower limit. You have to actually have it in the screen, right? So the lower limit here that I was using just a moment ago was 1. And my upper limit was 10, and if I select them, it actually shades it in, which is so cool to see, and that's actually why I wanted to show you what happens when it's not all the way to the edge, that it actually starts and stops where you tell it to. So another cool feature of your calculator.